Welcome back to Raw Green. Francesco and Emma here. Today we're talking about a very critical element of the energy transition, platinum.
And bacteria. So we've heard that bacteria can break down plastic, but metals?
Possibly they are slightly posher bacteria. So let's ask the people actually working on this. We're joined by Chris Morris and Patrick King from the University of Manchester. Welcome to Raw Green, guys.
Thanks for having us.
Guys, so it sounds like science fiction, but can we really extract or recycle platinum using bacteria?
Yeah, absolutely we can. It's something we've been working on over the last few years in our lab in Manchester. It's a really fascinating topic. We essentially use highly specialized metal-reducing bacteria which have the ability to respire metals in their natural environments. And then we sort of hijack this process in our lab, and they're able to take metals that are in solutions, effluents from industry, and under the right conditions can then precipitate, sort of chew up these metals from that solution and form these metal particles within their cell structure on their surface. And then we can use these for all manners of technologies. Obviously, recycling is our main focus at the moment, but there are also functional sort of nanomaterials we use them as catalysts. So there's a really interesting array of technologies that can come out of this.
We'll get into that. At the moment, where do platinum group metals, because there's a whole array of metals under this umbrella, where do they primarily come from?
Sure. So they're a critical mineral in that their supply is highly vulnerable, and the reason for that is they're only found in a handful of places in the world. So
North
primary.
Korea. Oh.
It's not quite that bad.
Yeah, luckily not there.
Okay.
So primarily South Africa.
Okay.
So there's the Bushveld complex in South Africa where primary mining of platinum is done. And I think that's the only location in the world where you can mine platinum as the primary target for mining. But these metals are very scarce, and so the rest of the metals. So we've got platinum, palladium, rhodium, ruthenium, and iridium. They're the five key elements that we're talking about today. And yeah, they're typically mined as byproducts from nickel mining primarily, or copper mining. And so, yeah, they're incredibly rare and incredibly valuable. They have immense financial value. People might recognize those elements from their jewelry. They're traded on all of the sort of precious metals markets. And then they have immense industrial value as well, which we can get into. So, yeah, this scarcity is one of the driving sort of forces behind
But it's not just for jewelry or other, let's say, expensive stuff. It is also for the energy transition.
Yes.
I read it is for lithium-ion battery production. It is for hydrogen. So if you can please break down on the energy transition side the usage of the platinum group metals.
Yeah, absolutely. The first thing to highlight is they're used across a huge array of industries, or almost every industry. Specifically for the energy transition, they're used to make a lot of key components in electronics. They're used to make turbines for wind farms. They're used in making batteries. I think specifically in making copper foils and things like that. They're absolutely critical to the hydrogen economy, so in fuel cells and electrolyzers and in the membranes involved in those.
Yeah, and it's also worth noting that a lot of the applications that we see being used now are just a small set of the possible applications. That so long as these metals remain scarce, there's kind of a siphoning of which industries can get their hands on them. But in the case where you would see one industry move away from using platinum group metals, or simply platinum group metals becoming more abundant, there's just a lot of people, both in research and directly in industry, who are kind of waiting to get their hands on them.
Well, what is fascinating? It is as you said earlier, they are a byproduct of mining of main other materials like nickel, copper, whatever other. So the fact that comes as a byproduct with that value, I've seen what is the cost per kilo, obviously of platinum, but also of the others. Was it the iridium that is 8,000-10,000 per ounce? So it is incredibly expensive. It is incredibly expensive. What I am curious to know, though, it is they are, as you said, classified as critical materials, right? What does that actually mean in practice?
Sure. So most sort of developed economies at the moment are producing these criticality reports on critical minerals. The UK just in December just published its most recent one. So that's a really useful framework to use to talk about these. And in that they specified critical minerals and growth minerals, which is a useful difference because criticality refers to the supply chain, the vulnerability of supply of these minerals, which are essential for technologies. Growth minerals refers to minerals that are essential for technologies where the supply isn't necessarily in jeopardy now, but as those sectors grow, exponentially over the next few decades, their supply, needs to grow concurrently with those. Interestingly, the platinum group metals are considered both a critical mineral and a growth mineral.
Wow.
Along with things like rare earths, which we obviously hear a lot about. We've touched on that they're only found in a handful of places, so they're super vulnerable to geopolitical issues around labor. If you think about, things like cobalt.
It's not just about the extraction. It is also the refining. And I don't know if this happens also with the platinum group metals, but I've seen it on phosphorus. There is no refining, of phosphorus in the European continent. And now they're restarting to revive that part of the supply chain. Does the same applies for platinum group metals, the refining?
Yes, so there's no mining, obviously, and then
Yeah.
mining and refining are quite linked. But what we do have is the recycling and refining.
There is recycling and refining.
Yeah, so the UK is very much like, one of the best in the world at refining the PGMs from secondary sources. And so that's really the emphasis within the sort of vision for PGM supply going forwards, is about improving and increasing that secondary supply. Your scrap catalysts from your cars or from chemical manufacturing or from electronic waste, collecting that as efficiently as possible. In some cases, like for autocatalytic converters, the recycling is already, very well done. Like I think the stat is around 95% is recycled. And that's really essential because the global warming potential from secondary supply is like 98% less than from primary supply. So on top of, so you're gaining so much from that. There's much less sort of environmental damage. You're increasing the sort of mitigating the supply chain vulnerability risks. It's a win-win.
So I'm not surprised that we're trying to find this stuff everywhere and recycle it where we can. But what are some of the biggest inefficiencies or fragilities in that current sort of recycling or supply chain system that you're aware of?
There's a few, I guess. The main. So I mean, a good example from recent years was 40% of the world's palladium comes from Russia. So when Russia invaded Ukraine, the palladium supply and pricings just went crazy for a year and a couple of years or so. Now palladium's an interesting case because it's the most diverse. It's found in the most places, still not many places, but more than the other PGMs. So the price was able to sort of flatten out eventually. But those shockwaves were definitely felt. And if a similar geopolitical sort of tension arose in, say, South Africa, then the world's platinum supply would suddenly, and iridium and rhodium and everything would become highly jeopardized. So that's certainly the most obvious one. I mean, in terms of secondary supply in the UK, I think the main issues are probably around, or the fragilities are around just the throughput of that. The UK is excellent at recycling, but the demand that's predicted to increase. I think in the UK's report, it was over the next 10 years, the demand for PGMs is going to increase tenfold. Is it realistic to expect a tenfold increase in the industrial sort of recycling, refining of PGMs in the UK? Like, yeah, that's going to be a challenge for sure.
And I think it's probably also just worth really considering how little we mine of some of the rarest ones. So if you take iridium, for example, and you imagine the kind of small 10-kilo bags you're allowed to bring on a Ryanair flight, and you multiply that volume by 7, that's roughly the amount that we mine per year of iridium, or that we refine. And you did mention that it's incredibly valuable, which it is, but that's such a small amount that value isn't able to drive the economics of the mining. It's always going to be the primary ore. So yeah, so that's just a very, very sensitive small chunk of this huge process, which, as well as being harmful, leaves us with kind of little wiggle room.
Well, look, what I, according to what you say and what I read also in your research, are some incredible stats that I forecast there is going to be a increase in hoarding of old e-waste. So these 3 facts, and please confirm this. So the UK has the second highest e-waste per capita, number 1. Number 2, there are 180 billion pounds of metals estimated in UK landfills. So now we're going to start to see queues in front of UK landfills. The third one, it is there are more precious metal content in anthropogenic waste that in remaining ore deposits. I mean, one, it is worse than the other. So we're literally going to start to ore stuff in here. Are all these 3 facts, is it confirmed?
That last fact is the one that surprises me the most. I suppose you'd have to have a very good handle on all possible ore deposits, which is quite challenging. But the other 2, I think, are quite solid, yeah.
Yeah, I think that one's maybe slightly up for debate, but certainly if you look at low-grade ores versus, say, the amount of palladium, for example, that's in, an iPhone or something, then yeah, you could definitely argue that point.
But imagining hoarding of e-waste is, it's a pretty vast amount of stuff to hoard. It's obviously constantly being generated. On the one hand, this would be
you
good.
Don't know my wife. You don't know.
Yeah, it would represent an awareness of the value in those products, which of course, would be good for general drives towards recycling and sort of suit our interests. But it's challenging when you just consider, how much there is and the very fact that it's growing. So the rate at which we're producing e-waste is growing around 5 times faster than the rate at which we're able to recycle it, or than the growth in our recycling capacity. So we have a long way to go before we're kind of catching up with the production of e-waste. But it's a vast amount of waste, and it's a vast amount of value that's kind of being tossed aside.
So let's stay with that for a minute, Patrick. If we're talking about urban mining, what does that actually mean in practice? This stuff's in small quantities and notoriously difficult to get hold of. What are you thinking there?
We can imagine the behavior change necessary for us to be properly siphoning e-waste, because we've already, done it with other forms of waste. And sometimes that's been tremendously effective in the case of, say, glass or metal cans. And sometimes it's been, a lot of effort on our behalf and not that much in the way of results in the case of a lot of plastics. Batteries is probably the closest example where there's pretty widespread awareness of the need to recycle batteries, and a lot of readily available facilities to do so. And then we can imagine sort of that process being extended to e-waste once the value is demonstrated. So right now, a kilogram of e-waste is equivalent to roughly 1.3 pounds in value. So that's already quite significant, for anyone who's going around trying to collect bulk. But if we could increase that value, then that would create a natural drive. And then, of course, there is the additional step of disassembly, which is going to be different depending on what product you've got. So there's an element of labor there in terms of extracting the parts of the e-waste that actually contain metal, which by mass is around half. If you manage to get to that far where we're extracting large numbers of microchips, essentially that kind of product, or copper wires, it's at that stage there's the final step where you've got this metal, that by value, roughly a third of it's gold, roughly a third of it's copper, roughly a third of it's iron, and from our perspective, for the kind of work we do, although right now we're not focused on gold, though the lab has looked at gold in the past, there's some kind of process needed to take very low concentrations of gold and agglomerate that into some mode that can be extracted. So, that step in the chain is where we would have the greatest interest, but there's no doubt that all the other steps can be achieved, I think.
Well, let's stay into the lab for a second, okay? I want to know more about your naughty bacteria that likes platinum. Okay? How does actually metal biorecovery? This is the correct definition, right? How does metal biorecovery using bacteria actually works?
Yeah. So our method that we're working on uses metal reducing bacteria. So these are bacteria that are found naturally in the Earth's subsurface. They were isolated a few decades ago, and people have been using them in the lab ever since. And they have this really cool quirk where instead of breathing using oxygen like we do, when oxygen's not around, they can breathe using metals instead. Yeah.
Heavy breath. Yes.
Yeah. Which is, it's very cool. So, I mean, if we think about respiration as fundamentally an electron transfer process, then the simplest way of thinking about it is that we generate all this energy, and then we have to dump our electrons from almost as a waste product. We dump that into oxygen, and that's the most efficient way of respiring, and that's why so much of the world's life respires that way.
Survives. Yeah.
Yes.
Yeah.
But life is very diverse, and when oxygen's not around, there are organisms that thrive by using more creative methods. So these bacteria dump those electrons into metals. So in their natural environments, that would typically be iron oxides or manganese oxides, that some of the most abundant metals in the Earth's crust. But like I said earlier, we can then hijack this process. So they're just looking for a metal to bind to and to dump those electrons. And we have experimented a lot across the periodic table and have found a vast array of these metals which it can perform this with. And luckily for us, some of the most favored metals are also some of the most valuable metals. So the precious metals, the PGMs, along with gold and silver, are some of our bacteria's favorites, which, very expensive taste, as you said.
But you said we're isolated 10 years ago, okay?
Oh, no, sorry, decades ago.
Decades ago.
80s, maybe. Yeah.
What I want to know is how do you grow and maintain these bacteria? They're not like pets, okay? So, and how do you grow them at scale? What conditions do they need? Do they need a particular set of nutrients, I assume, too, or temperatures and conditions? And I don't know if you can please break it down a little bit.
Yeah, sure. So it's worth saying that the bacteria that we've chosen to work with has a lot of advantages in this regard. So it's called Shewanella, the bacteria we work with, and it has a really diverse metabolism. It can grow in many different ways using many different substrates. So that gives us a lot of flexibility in how we design our process. So some of these bacteria will only grow without oxygen. Our bacteria can grow aerobically, so with oxygen. It can grow to very high density aerobically, and then we can switch it into an anaerobic sort of mode where it can start respiring metals. So that's a big help. But yes, you do need a specific media to grow it on. So there's certain substrates it will like. So for instance, lactate is its preferred sort of molecule to grow off. So that's a simple sugar. So like, we typically like glucose, for example. So we all have our preferred tastes.
And what's the feedstock then in terms of actually getting the, let's say, e-waste into that sort of container with the bacteria? How do you need to present it?
In theory, there's lots of ways we could present it. If you look at these bacteria in the wild, they'll often grow directly on the metals that they're interested in targeting. So, like I say, in theory, it's possible to do it in a variety of ways. what we're actually working with now is an effluent which consists of metals that have been dissolved in really just acid, really strong acid, which can allow a solution to be prepared where there's a mix of all these different metals, which is kind of a nightmare if you're using standard methods to then selectively extract the different metals from. But that's exactly kind of what we can train the bacteria to do. And as you were saying earlier, Francesco, I mean, right now we're working with Shionella. They're great. They're very robust. In the natural world, oftentimes there's lots and lots of different bacteria that are operating in these kind of mixed metal soups, and they're all kind of passing electrons off to each other, and ultimately it's being expected by one of these target metals.
Well, I was going to ask, what's the bottleneck in that case? What's stopping scale at pace at the moment?
That's an interesting question. I mean, when you think of a bottleneck, you're typically thinking of something, something very, very concrete, a particular material that we don't have enough of. And there really isn't something like that we can clearly identify. I would say that in a strange way, a bottleneck for using this in the long run and for lots of different industrial, biotechnological, or synthetic biology applications is kind of complexity. Everyone knows that these things can be done in theory. Everyone knows that living systems are capable of achieving these goals. It's just that when you start working with it, and especially in the past when we had, a limited ability to work with some organisms. So when I say that there's lots of organisms in the wild that do things like this, we can't culture a lot of them. But we're making advances, and not in a linear way, in a kind of exponential way. Our ability to sort of understand these systems and therefore to manipulate them is kind of taking off. And, some of that is down to just biological methods, and some of it's down to bioinformatics, our ability to sort of process the data related to these systems or to engineer different proteins. And so it's as those abilities take off that kind of complexity bottleneck, our ability to understand and manipulate the system, is kind of breaking open. And therefore, well, in terms of hard material bottlenecks, there isn't an obvious one at present.
But there is also an efficiency one. There is also an efficiency, related to processing. I went through your LCA, which is really, really, really well done, and very clear in terms of the results, and the beauty of the outcome of your research. It is that it can give you a direction of where to concentrate to move to different levels of TRLs, of your technology. And one of these was the volumes that primary mining and secondary recycling are managing, are processing, compared to obviously what it is right now, lab level and lab technology that you guys have developed. But at the same time, there is something that we have absolutely not discussed, which are, what if you are extremely successful? You say, in 5 years, you deploy the bacteria at scale. You're able to very efficiently refine platinum and all the other metals part of the group. What are the risks? What happens if you have a river of these bacteria?
It's important to emphasize these are category 1 bacteria. They're not harmful, they're not pathogenic. So there's no horrendous immediate sort of risk to the wider world if they escape. One aspect of the project is engineering biology. So to get the most efficiency out of this system, we envisage genetically modifying the organism, which obviously immediately sets off alarm bells for certain people, rightly so in some cases. But this is precision gene editing. So this is increasing or decreasing certain pathways, certain enzymes that the bacteria already possesses. We don't envisage this being, a potential sort of risk if it escapes. And these are also bacteria that are being grown for a specific purpose in hazardous sort of waste. So they're not going to be particularly fit if they escape for general life, because we'll have specified them to that environment.
You've seen the quality of our rivers, right?
Well, that's a good point.
Yeah, and I think another part of the industry to keep in mind, or a related industry, is bioleaching. And it addresses both the question you raised earlier of scale. Can you really imagine this lab process, producing the kinds of volumes that we'd be concerned with? And if you look at a metal that we produce vastly more than any PGM, copper, at present 10 to 15% of the copper supply is provided by a bioleaching process, which is a demonstration of the capacity for scale. It also relates to your later point, which is that bioleaching is a process that isn't anywhere near as contained. Certainly in the case of these vast pits where you have ore basically resting within a culture that's been seeded and is allowing the metal to be extracted in a more mineable form.
I believe what you say 101%. I read about the Department of Energy in the US that invested, I don't know how many billions, to set up a fully AI automated facility just for the development of bacteria. So I know there is a lot of interest into the area quite aggressively. Let's just ask you now about economics, and we only want to know confidential information, obviously. Where do the projected unit economics make sense, and where do probably not?
So I think the key thing for us is, certainly in the context of the PGMs and the precious metals, we're talking about very high value and relatively low volume effluent waste streams. As we're still at sort of lab scale, it's hard to give projected economic cost savings and profits and losses and that sort of thing. But where we envisage making that big economic step forwards is that we can essentially create a market around energy saving. I think I mentioned already that we're very good at refining platinum group metals in the UK, across Europe, but we are limited by the cost of energy because the process of recycling, especially the effluents, where the existing technologies become orders of magnitude more inefficient, the energy cost of recycling becomes very high. So that's where we envisage making huge savings, and that's also, without having access to the information around those costs specifically, it's hard to give exact numbers. But yeah, so increasing efficiency and doing it more sustainably are our two main goals with this technology, and we envisage it as a polishing step on top of current refining processes, and with the use of bioreactors, eventually, we envisage it becoming something of a modular technology that you can license out and bolt on the end of existing processes. That's our vision at the moment.
Good. And I work with other startups that are trying to do similar things, particularly, of course, with the size of the e-waste problem. So talk us through some of the other alternatives that do exist with regards to the chemical or the sort of electrochemical sort of recovery of metals in this space, and how your methods do work with, as you say, or compare against them.
Yeah, so the most commonly used methods at the moment are solvent extraction, so using non-aqueous, quite chemically demanding solvents to selectively switch metals between solutions. Ion exchange, where you have highly engineered resins which have certain properties which again selectively collect those metals from solution. You have electrowinning, which is an electro deposition technique. But these again become quite inefficient in the kinds of waste that we're talking about, to the point where they become economically not that viable necessarily, where we're talking about low metal concentrations and highly complex solutions with many different metals and impurities. And then there are other startups that are trying to do similar sort of work, but with chemical systems. They're not employing bacteria, and they're using things like polymers or functionalized silica to try and selectively recover these metals. From what we can tell, they're sort of aiming more at the mining sector or the chemical manufacturing sectors. We don't know how well their sort of technologies would work on these effluents that we're specifically talking about. And just to reiterate, we have these effluents in our lab, and our technology is recovering PGMs from them. So we know that we've got something that works in that regard.
And one thing I'd add is, a lot of these systems can be very effective for one particular metal, or sometimes for groups. And every company or startup as it scales up is going to get economies of scale in terms of whether you're manufacturing a polymer, or for us, if for the feedstock we were providing to grow our bacteria. One advantage that we have, which is going to be unique to systems that use some kind of living component, is that with every scaled up facility, we can continue to select for the strains or the communities of bacteria that are proving to be the most effective. And so we don't just get a reduction in cost as we grow, we get a kind of an improvement in performance that doesn't really have a ceiling, right? Exactly.
Yeah.
And that applies to efficiency of gathering the metals, but it also, again, can apply to the production of products, some of which we've already kind of looked at in the case of catalysts, but some of which we haven't considered yet. You know what I mean? There's just this flexibility in the system that uses bacteria that doesn't exist necessarily if you're using a polymer or some kind of electrochemical approach.
But once you reach, let's say, a number of iterations, you can also work, for example, on grade output, on the metal grades. You can focus on that as well. So, I mean, the way you can approach this, the angles you can approach, which once you have that bulk of data that you can manipulate or play with it, it's extremely fascinating. It really is extremely fascinating.
And it's exciting. You know what I mean? It's just it's a very kind of, it's enjoyable to have a kind of partner with these bacteria where, you know, you don't know exactly what they're going to do, but, you know, there's...
They don't ask for alimony if you divorce. So it's fantastic. So what's next for you guys? You're currently TRL 3. So you run your trials, you're done your LCA. What's happening after that?
I mean, we're currently still in a pretty intense process of development R&D, in terms of we have a system that works, but we need to make it as efficient as possible. So that's our immediate goal. But then we're starting to enter the sort of accelerator programs and build our spin out over the next year, 18 months. That's
Emma's bread and butter. Yeah.
Yeah, and we're just aligning the research goals with the scaling goals, I think, is another thing, is that we're, you know, there's still plenty of papers to be published, plenty of just interesting things to find out about these systems. But increasingly, we're trying to align all of those goals with, you know, what is needed to make these systems more viable, more scalable, and really focusing on using the same kind of, you know, presentation of the metal that we would see in the cases that our industrial partners would be interested in.
Have industrial partners reached out to you yet? Has anyone shown any specific interest?
So our work is very much in collaboration with Johnson Matthey, who are a big PGM refiner, and yeah, that's who we would like to sort of go forwards with in that regards, and then it's about reaching out to as many people as possible across the precious metals industry to start with, and then moving on from there as well.
That's a great partner, and they could probably take you all the way if they wanted to, so that's exciting. Yeah, nice. So realistically, once this has actually been deployed and it's perhaps operational and commercial, what's next? Do you see the next cliff to climb with regards to developing bacteria specifically?
Yeah, I mean, obviously it's a pretty big initial step, right? So the PGM market is already tens of billions, as we've discussed before. The e-waste situation is also in the tens of billions per year in terms of value. Now, I one of the reasons when I decided to go into this area, I was looking broadly at metal recovery using biological methods, and as we were discussing before, bioleaching, having demonstrated real value, is kind of an exciting area in and of itself. I think that it's worth noting that in those systems, they typically don't use engineered bacteria. They typically just rely on the native abilities of bacteria that will grow in these environments anyway. So if we've developed a lot of experience, creating hardy strains that are particularly optimized, I'd be very excited about moving into those kind of larger scale mining environments as well. So not just in the refining or secondary refining, but being able to go out. And this is, I think, as the demand for metal grows massively, it's happening at the same time that the tolerance for mining is going down, right? So recently enough, there was a massive lithium deposits that were kind of explored in Finland, but they're struggling to open the mines, and everyone can understand why. Nobody wants mines going up near them, and increasingly good, thankfully we care about the people around the world who are suffering because of the expansion of mining operations near them. So I think that this, more broadly can be seen as a way of replacing methods that require moving huge amounts of material on Earth and harming the lives of people near them, while acquiring these essential and valuable materials.
That's very good also from an environmental perspective.
Yeah. And also, thinking into the future and more broadly, I think developing a wider bioeconomy, circular economy for metals. So like we've mentioned bioleaching. So bioleaching is a brilliant way of getting metals into solution, and then our technology is a great way of getting them out of solution again in a more purified form that we can recycle. So I think linking up various biotechnologies to work in harmony with each other is a really exciting idea.
Wonderful. Well, thank you, gentlemen. This was very, very interesting. The potential, it's just huge. It would be good to see how you guys progress with the next stages of your research. And thank you very much for participating on Raw Green.
Thanks very much for having us.
Yeah, thank you. It's been great.
Catch up soon. Ciao.
Ciao.
Thanks for listening to this episode of Raw Green. If you made it this far, you probably enjoyed it. So don't forget to hit subscribe and follow our podcast. It's an awesome way to support our community. At Obi, we're all about research, life cycle assessment, and the green tech innovation. Stay in touch through our socials or visit our website. Links are ready for you in the description. Catch you in the next episode. Ciao.